So, for today's lesson, we're going to learn about something called relations. And the first thing I want to really just hammer home before I go into the more formal concepts of this lesson is that all a relation is a set. And what a relation specifically is a set of tuples. So, it could look something like xy, yz, ab. And this is an example where it's all tuples of size 2, but it also could be a set of tuples of size 3. So this could be one relation, R1. This could be my other relation, R2, a different relation. And this could be like XYZ, ABC, and so on. And the main property that a relation has is that for each tuple, the elements within the tuple have the some type of property in common relative to each other. So what I mean by that is for like in this uh in this first set R1, X and Y relate to each other the same way Y and Z relate to each other, and the same way A and B relate to each other. So it could be something where it's like they could all be like M less than N, where like, so that would mean like X is less than Y is less than Z, and A is less than B. So like they just relate to each other given some property, and it's all the same property, and it's all like ordered in this way. And similarly, you could have it for like three elements. So you could have it like uh, M plus N equals P. And then you could have, so this would be like X plus Y equals Z, A plus B equals C, something like that. So the idea is a relation is just this set right here of tuples, but there's some kind of property binding each of these elements within these tuples. And so I'll go more into like formally what this means, but I just want you to kind of keep that idea in mind that like a relation is a set of tuples. Okay. So now I'm going to talk about them in a more formal way. And so the idea is a relation on two sets. A and B is a subset of pair, which is the Cartesian product of A and B, right? And so what do I mean by that? So mostly for what I'm going to be talking about in this lesson is we are going to be talking about relations on two sets. So that's going to be the idea that, this is like we're going to have these tuples of size 2. So this example that I had previously of like XY, YZ, and AB, we're generally going to be talking about tuples of this size, just like going on, because most of the relations we're going to be talking about are going to be more like that kind of like just comparing two elements or like how two elements relate to each other. So we're going to be having these tuples of size 2. Um, and the way you typically define them is you basically say, okay, I have my relation R. It's going to be equal to this set of tuples, M and N, such that, and then the first part's usually going to be something about like what set M and N are from. So if I want both M and N to be integers, let's say, and then I'll say M and N are in Z, right? This is my symbol right here for the integers that we learned. And so I'll have like that first part saying like what set they're in, and then I'll have a conjunction, and then I'll be saying something usually about like how those items relate. And so this is as I was talking about in the previous slide, where like, okay, so each of these elements are going to be in Z, and M is going to be less than N. So if M is all the M's are in Z and the pair is MN, that means this is in Z, this is in Z. I'm just saying Z, but that, means your integers. And similarly, if N's in Z, then that means that this is in Z, right? Because this is the second part of my tuple. So this is in Z, this is in Z, and this is in Z. So that's basically like this first part is just telling me like what set each of those elements of the pair is from. And then the second part is telling me how they relate. And so this is what we were talking about previously, like in the example I gave previously where I did like, it's going to be a less than relation. So it'll say X is less than Y is less than Z, A is less than B. Okay, and so, similarly, I could say maybe something like, so if I said something like N is less than M, like I just want to be clear how order kind of matters here. right? That's something different, right? Because I have the ordering of the pairs is m, n. So if I say n is less than m, that would be saying, I'd be basically flipping it around. I'd be saying like y is less than x, z is less than y, b is less than a. So I just want to make sure like we're kind of clear about how like this ordering ties in here. Just so, and in general, you want to kind of keep it like following your ordering so that way you don't get that kind of confusion. And so the first question I have here is like, okay, so what are the two sets that I'm looking at? Because this relation is really a subset of the Cartesian product of two sets. And so what this really is it's a subset of the Cartesian product of the integers. What do I mean by that? It's all, so remember when we were talking about like sets that are kind of like, when we were talking about like tuples and you have like two items, they're going to be like in z squared, right? Because it's going to be like in the Cartesian product of the integers. And so that's what we're kind of talking about is this will exist in z squared because like the first element is in z and then we're taking the Cartesian product and like, right, this is like where m's from and this is where n's from. Oops, sorry. And this is where n's from. And so we're taking like the Cartesian product. And so that's why like they exist in the Cartesian product of z times z or z squared. So if like I said, m is in z and n is in r, then I would say like my set is z times r. In other words, right? It's a Cartesian product of the integers and the real numbers. And I'll give more examples of this. I'm just trying to kind of get you familiar with this notation. But this is just the general idea of a relation and how it kind of defines the elements within it and the kind of syntax we'll be seeing when we want to define these relations. Okay, so let's keep looking at this relation. So we can kind of think more about it. So we're still talking about this relation where it's m and n are both integers, and m is less than n. Okay. So in English, right, it's just all pairs of integers mn such that m is less than n. So if you want, like, if it's easier to translate it into English first, that's always a good thing to do, if that helps you. And so my question is the pair 2, 3 in R? And so the answer is yes, right? Because 2 is an integer, 3 is an integer. Sorry, so this is really supposed to be like more of the z's kind of look funny here. This is like your set of integers, z, right? So it kind of has like your two lines, you can imagine. But since 2 is an integer and 3 is an integer and 2 is less than 3, that means that this property up here holds. And so we're good. This means that this it would be this mn in this set R. So one way you could say it is this is 2, 3 is in R, because this relation kind of, you can think about it as this relation describes this pair 2, 3. Now, another way I can say like something is in R, like another common way you might see it is something like 2R3. And this is just another type of syntax, but this is saying the same thing. So these are saying the same thing, that like this relation R exists between 2 and 3, and so you're kind of just like writing the R in between. So that's just another way you could describe it if you wanted to. Okay, so now my next question is the pair 3, 2 in R. And that's no, right? Because even though like it is this first part's true, right? 3 and 2 are both in integers. They're both in the set of integers. 3 is not less than 2. So this property here doesn't hold. So they are not in R. And so you also could like describe that using that previous notation where you could say 3 does not have that relation between between 2. And so notice like that we do have that kind of like that property, right? Like where you can have 2R3 but not necessarily 3R2, right? Or like 2, 3 in R. but like 3, 2 is not in R. That's kind of like interesting, right? Like you can have the same numbers, but the ordering does matter because of like how we ordered this rule. And so we can use relations to describe many different types of relationships. So, like right now I was just showing like a less than relationship, but let's go back to like our coin purse example. So remember that we had this set C of coin purses. So this is from the practice problem I did last week. So you have your set of coin purses C, and X is your set of coins, and you had this property that this like predicate in, and basically in's true with like X and C if coin X is in coin purse C, right? So basically this is just telling you whether or not coin X is in coin purse C. Well, we can like actually describe that as like we can make the set of all coins that have a coin purse um basically like using that in predicate. So in other words, we can say like our relation R is going to be the set of all coins and their related coin purse, where that so we're saying, X is in X, so X is a coin, C is in C, C is a coin purse, and X is in C. So this is another like just type of relation. We could have the pairs, all like pairs of coins and their associated coin purse. And this is how I would define that relation. And so these are things I've already kind of hinted at, but I just want to kind of like hammer it home again. So most of the relationships we'll be talking about will be binary relations. So that's what I was talking about, where it was usually like tuples of size 2, and you'll be having like you'll be kind of showing it as like two sets, like as a subset of two different sets, right? So we had it as like the subset of like Z cross Z or Z cross R or whatever. And the idea is because you have tuples of size 2, right? And so this is mostly like the type of relations we're going to be talking about are going to be this binary type. But as I showed you in the first slide, you can have relations of bigger sizes. And this is something I also said, but another way we might want to say something in terms of a relation is instead of saying like that X and Y is in R, you would say X, R, Y. And so I just wanted to kind of reiterate that property as well. So there are other ways you can show relations. And generally, I think it's just kind of depends on the example, which way is the easiest way to view the relation. And so one way you could do it is by doing like a more graph kind of format. And so you could just make like every like element of A and B a dot or a vertex, and draw an edge with an arrow for each A to B. So like if I wanted to do like a graph of like this is what I made doing a homework problem. And basically you have like M and N where like the relation is do M before N. So like I'm always going to do this thing first, and then this is the next thing I do. Do this thing first, and this is the next thing I do. And so this is actually a relation, is like defining a flowchart is actually like with a relation. And another thing I want to say about this is like often a way you'll be doing this though is you'll be making it more like a graph where like you'll have like if it is going to be like A and B, like over the sets A and B, often what you'll do is you'll have like one row A and one row B, and you'll have like the elements of A like X, Y, A, and the elements of B, so it's like Y, Z, little b, and then you'll have like the arrows drawing like where the relation holds. And so like often this is a way you'll see like graph representation of relations, not necessarily like in this flowchart form. So like in your online lesson, you're going to be doing something that looks a little more like this, where you're kind of like drawing this arrow, and each arrow means like just like that relation holds. And it doesn't necessarily need to be like one-to-one like this. Like it can be, like if I am doing like less than, say like if X is less than Y and Y is less than Z, then like X is also less than Z. So we'll have this arrow of like x going to z as well, because x is also less than z, so that's also true. So like you could have like multiple arrows, coming from one element potentially. Or you could have no arrows. Like if A is not less than anything, then you could have no arrows from A. But if we did say that A was less than B, then you would have that arrow. Another way you could write relations is with a true-false matrix. And so basically what you do is you put like the elements of the first set on one side of the matrix. So like this could be, like these could be like this side, oops. Like this side is A, and this side is B, and then usually like this part is going to be like a relation. So like this one, instead of a less than, I did like equals. So like they're only in the relation to get if they like equal each other, right? So like this equals relation for like R, where it's pair X, Y, and you have the numbers 1, 2, 3, 4. And so X and Y are both in this set. So that means that your A, like your set A, is 1, 2, 3, 4. And your set B is 1, 2, 3, 4. And then you could just think of it as like X is in A and Y is in B. Like if that's how you'd rather think of the way like you're defining it. And basically they're in this relation if X equals Y. So that means like R would be, in this set, it would be like 1, 1, 2, 2, 3, 3, and 4, 4. So it's all elements that equal each other. So this should actually be like kind of this set squared, because it's really like two sets, but that's okay. Either way, either type of definition is fine. But yeah, so this would be like all elements, right? Where like, so this is X and Y, where X equals Y. So that's 1, 1, 2, 2, 3, 3, and 4, 4. So in my true false matrix, if I wanted to show, like, again, say that X is in like this A and Y is in this B. And so this is A and this is B. Then you could generally like just for each element, basically like what you do is if that value for X and that value for Y are in that relation, then you put a true. So 1, 1 is in my relation, so I put true. 2, 1 is not in my relation, so I put false. 3, 1 is not in my relation, so I put false, and so on. So like for 2, 2 is in my relation, so I go like 2, 2, that's this square, and sure enough, that gets a true. So this could be just another type of representation, is with this like true false matrix, just showing existence, like whether or not this element exists in this relation. Now, some of the things we're going to be learning about relations too is just going to be different like properties they can have. And a lot of these things aren't going to be described using first order logic. And so the first two things I want to talk about are these kind of like different versions of, or like a modified version of a relation. So say I have an existing relation R, I could create the complement of R. And that's just basically all pairs that are not in R. So if I was doing like that previous set where I was doing like all pairs where like X equals Y is like my R, then like I would basically have all pairs where X does not equal Y as the complement of R. So like R, the complement of R would be like 1, 2, 1, 3, 2, 3, and so on. So basically all pairs that are not in R. And so this is the idea of the complement. Often what it'll do is it'll just like usually in this like last part of your definition where you're kind of talking about the property, you'll just kind of like flip that and make it the opposite, or you'll like logically negate it, right? So instead of like, so like X, Y, and R for this one was like X equals Y. And so I would just like negate that by saying like X does not equal Y. And so often it just means like negating this last part of that statement. And so the inverse is obtained simply by swapping the order of every pair. And so like on that first slide where I was saying like where I had like um A, B, I think I had X, Y, Y, Z. So like the inverse of that set would just be B, A, Y, X, Z, Y. Oops. And so like if this were still R, like so this is my R. And remember I just did this where like it was like M is less than N. Basically like the inverse, like this would still be true, but now I have like that different ordering. So like I can always say like this is the same set, but now it's like NM. So this was like MN. Or like M is less than N, I could say like this is NM, where N is greater than or equal to M, right? Because if M's less than N, N is greater than or equal to M. So like they're saying the same thing, I'm just kind of swapping their orders and kind of just like flipping these two this property, or saying, like the opposite of it. And so that's the idea of the inverse, is like these properties, like these are the same thing, right? So you could have the same property, so, or I could literally just keep it as like, instead of like, I could just literally keep it as M is less than N, but the order of the pairs is NM now. So it's not really changing like this property, is just changing the order of the pairs. And so that's the idea of the inverse. So if I have a group of coworkers, Alice, Bob, and Chris, and I want to create a relation where it's like Alice sends an email to everyone else, and say Chris replies to her email. So if my relation R is A and B, such that A and B is in P, so P is just my set of people, and A sent an email to B, so that's my second property, right? A sent an email to B. And so you'll kind of already be able to think about like, okay, what will the elements in this be? Alice sent an email to everyone. So you'll have Alice to Bob and Alice to Chris. And it also says Chris replies to her email. So then you also know you'll have like a Chris and Alice pair, because Chris sent an email to Alice. So you can kind of think of that as like, that's how I would form this set R. So the complement would be the set AB where A did not send an email to B, right? The complement is just literally everything that doesn't exist, all the other pairings that don't exist in this set. So that would be like, Bob didn't send anything to Alice, Bob didn't send anything to Chris, and Chris didn't send anything to Bob. So that's my complement. And the inverse is the set BA where B received an email from A. Same thing as A sent an email to B, right? We're assuming our email works, and if you send the email, it makes it through. So you could say B received an email from A, or you could still say like A emailed B, but it's the set BA now. So it's literally just this set, right, but flipped. And you're kind of just thinking about it more in terms of like, okay, who received the email from who, instead of like who sent the email to who. And so a lot of binary relations also are going to happen over a single set. And so this was like what I was talking about previously over like the integers. So like, like you have a lot of different properties like over where like, X, oops, where like X and Y, where like X and Y are both integers, something like that. And so it's basically like it's happening over like Z times Z. And so we're going to talk about some properties that like binary relations over the same set. Often like we're going to be talking about it in terms of like integers or real numbers, something like that. And remember, this could also be written as Z squared. This could be written as R squared. So like often it'll be like a set of numbers. And so it'll just be like, these are different properties we're going to talk about for relations, but it's where like both elements are from like the same set. So the first type I'm going to talk about is a reflexive relation. And so basically what that means is that like a property holds like an element has that property on itself. So like that property holds for I think it's best way to show an example. So if I have this set R equal, I called it like equal so we know like this is specifically describing like elements that are equal to each other. So I have a pair XY such that X and Y are integers and X equals Y. And I'm asking, is this reflexive? And yes, because every integer equals itself. But if I'm talking about like the set, and so this is what I was talking about earlier, right? This was my set like where I had, like 1 1, 2 2, and so on, right? And so sure enough, like 1R1 is true. 2R2 is true because so like basically what it's saying is XRX is always going to be true because X equals X. So like that's true. We're good. And so if I wanted to go like in this one where I'm saying X and Y, where X and Y are integers, but X does not equal Y. So this would be that set that I was talking about where it was like 1, 2, 2, 3, and so on. Then I won't have like 1 R1, right? Because 1 1 won't be in here. Like 1 1 is not going to be in this set because 1 does equal 1. So it's not true that 1 does not equal 1 in other words. So it's not going to be true that X Rx or X does not Rx is another way you can say that. So this is not reflexive because we don't have that property. So every integer X does not equal X is not true, right? It's not true that everything doesn't equal itself. Everything does equal itself. So this is just an example. And so remember, this property could change, right? So, we'll get more practice with this. But like this could be for any property. It doesn't have to be necessarily for like equals. So like maybe another example you could have actually, like just to make sure we're hammering this home, because I sometimes see people think like, okay, this means it has to be equals. It doesn't have to be equals. Like it could be like another one that could be considered like if I did X less than Y, right? Like that's not going to be reflexive, right? Because X is not less than itself, right? But if I did like X is greater than or equal to Y, that is going to be reflexive because X is greater than or equal to itself because X equals itself, right? Or something like that. Or like X equals the square root of X squared, right? Like maybe that's the relation I'm talking about, or X equals the square root of Y squared. Then like, for X Rx, that would be true because X does equal the square root of X squared. You simplify that out and you just get X equals X. And so obviously you're kind of thinking about pluses and minuses here, which we'll talk about a little more later. But like in general, like this reflexive property doesn't mean that they're necessarily equal. It's just that like the relation will hold for like the same object. So like it just means that X Rx holds. And so when you're checking for these properties, I think it's always best to just like go back and like look at these definitions and just plug it into the definitions and don't get like so bogged down by the examples. This is just like from what I see people getting tripped up by is like I see people getting tripped up by this like equals, and that's not really what we're talking about. It means you're really checking like X Rx. And so like really go back to these like definitions and make sure you can plug it in, and that'll be a better like path towards success. Okay. So we have reflexive, so we also have irreflexive. And basically that just means that like for every element, X Rx does not hold. So you will never find the pair XX in the right. So you will not have X Rx. And remember, this is the same thing as saying like the pair XX will be found in your not your real numbers, but in your relation R. And so basically, you're saying like you will never find the pair x, x, and r for any x. And so again, we can go back to our example like x and y, where x and y are integers, and we're seeing if x equals y. So x r x, well, like you are gonna find that to be true for every x, right? So you're gonna find a counterexample. You're gonna find a place where this is not true. Like 1 is gonna be an r. So that's like, you can think of that as your counterexample. So it's not true that for all x, xrx does not hold. So therefore, no, it is not irreflexive. So for irreflexive, it has to hold for every element. So no, because for all integers, x equals x holds. What about the non-equal? This is irreflexive, right? Because for all integers, it's true that you can't say something doesn't equal itself. So this is going to be irreflexive. Now, another property you'll see is symmetry. And this is something I was kind of talking about before, where like we're looking at a set and we see the pair xy in R. That doesn't necessarily mean yx is in R, right? Because that's not necessarily true, right? Like, especially when we have like x less than y, then it's not going to be true that y is also less than x. So if this is an R, then, like this is not going to be an R. So basically something is reflexive if it is true. If you can kind of change the order and both orderings are going to be in R, which, does happen. A common example here is going to be like this equals, right? So if x equals y, you can also say that y equals x. And that's going to be true for anything, right? So for equality, it is symmetric because if x equals y, then y equals x. What about non-equal? So if x doesn't equal y, is it true that y doesn't equal x? Right? So xry implies yrx. So basically you can think about it like x does not equal y. Does that imply y does not equal x? Right? And that's true, right? If this doesn't equal this, then this also doesn't equal this. So so non-equals is also not symmetric, or is also symmetric. What about our less than symbol? And so this is what I was talking about previously, right? Where if we have like x is less than y, we can't really say like y is also less than x, right? That's not going to be true. So, we're not going to have a symmetric relation for x being less than y. For y being, for this less than relation, in other words. And so similarly to reflexivity, we have like this anti-symmetry. So something is anti-symmetric if this is always true that like we cannot flip it. So this is basically like we can never flip this ordering. So if and so this, like if x and y is in R, I feel like sometimes this notation, so remember this is just saying xy is in R implies yx is not in R, and that's always true. So if like 1, 2 is in R, then like 2, 1 is not going to be in R. And that's like always going to be the case, right? And so that's the idea of, anti-symmetric. It's always the case that if like this is in it, then the flip is not going to be in it. So for our less than operation, we have xy. And so you have your pairs xy such that x is less than y, right? And x and y are both integers. So is this anti-symmetric? This was the example we were just talking about. And the answer is yes, right? Because for all x and y, if x is less than y, then y is not less than x, right? Y is greater than x. So it's not going to be true that y is less than x. What about less than or equal to? So this one's kind of interesting, right? So very similar, we have x and y, where x and y are integers, and x is less than or equal to y. And so What about, so sorry, so yes, this is anti-symmetric because if x is less than or equal to y, then y is not less than or equal to x. But wait a minute, I said this had to hold for all x and y. And but if x equals 2 and y equals 2, then like we do kind of like this is contradicting me because I'm saying, okay, so if like 2 is less than or equal to 2, it's also true that 2 is less than or equal to 2, right? Like I can flip it. And so both of these are going to be an R. But in this definition, I say it's anti-symmetric for every non-equal element. So this is why I can still say that less than or equal to is still anti-symmetric, because I'm not counting these instances, because it's only for cases where they do not equal each other. So for transitivity, this usually will, this has to do with 3 elements within your relation. And basically what you're saying is like if x and y have a relation and then y and z have a relation, then x and z should have that relation. And so, you know, in other words, again, if we wanted to write it like this way too, you could say if x and y are an R and y and z are an R, then x and z must be also be an R. Like this tuple must also exist in my relation. Um, and so, you know, we can think about like our other examples. Like, so, you know, like the thing I was talking about previously, if like x is less than y and y is less than z, then we know x is going to be less than z. So like this is transitive, right? This is like a transitive property. And so similarly, like let's talk about equality. So if x equals y and y equals z, does x equal z? And yes, right? It is true. X does equal z. So that means that we do have a transitive property here. And so these are all of our properties we can talk about with our relations. And so some of your assignment is going to involve kind of proving these properties. So you just want to, again, like my best piece of advice is to just always like go back to these definitions and just like plug them in. Like think of your example, like think of what X, Y, and Z are, think of what like X, R, Y means and what X, Y, R, Z means, like all of that. Like just go back and plug it into your definition and see if it's true. And then I think you'll be fine.